This video I'm going to be talking about AC reactive power, and this is going off the basis that P equals VI from our original DC type of circuits. So for reactive power, we have Q is the variable, and this is from inductors and capacitors, which are constantly storing and releasing energy. And we use the equation VRMS times IRMS times sine of theta, the angle. So it's the same in DC for V and I. It is V and I here, except VRMS and IRMS are basically averages when we're thinking of RMS. That's the closest average we can get to something that's variable in time, as this explains. And then the other thing that we have here is average power, which is just from the resistors. This is mostly constant. It again uses VRMS and IRMS cosine of theta. And these two are basically the averages that we can get, and then sine or cosine of theta is once again just the time factors for AC. Those are the two equations that we get. And then that leads us to complex and apparent power. So complex power is just a combination of both average and reactive power. Reactive power is our imaginary with our J's, and apparent power is just the magnitude of those. So kind of looking at our triangle over here, complex power is both a combination of our reactive and our average powers and apparent power. And that follows the same idea as our complex resistance, which we understand with our real resistance and our imaginary inductive or conductance resistance, leading to our total impedance, which is R and Z. So that follows the same idea. Multiply by R to get to voltage, because R times I equals V. Multiply V again times I gives us P. So all three of these are following the same idea, but now instead of being resistance, it's at P for power and from resistance. Now instead of being Z, it's at Q for power, which is variable from our inductors and capacitors, and now it's apparent power, which used to be our impedance, but now it's apparent.